Continue with the concept of logistic regression. Given a data, we have data samples from 1 to n, and each data sample represented by xi and yi, where xi is your predictor variable and yi is your expected outcome, and this is the predictor variable. You can have multiple variables as the predictors, where x can take the value from 1 to d, and in logistic regression y can only have the value 0 or 1, and we need to find the regression coefficients w0 to wd that minimize the classification error, which is the squared error. And our h of x classifier function is defined by 1 divided by exponent of f of x, and f of x we are familiar with. It can be represented in this format, where x are the variables and w's are the regression coefficients. Now we move on to gradient descent. So what is the gradient descent method, and how can we find a solution or optimize our solution using gradient descent? We have to find an f of x that is the best discrimination between the classes 0 and 1. So as we did before, we take the derivative partial of your function h of xi minus yi, and here I would like to mention that we are going to use the chain rule. I hope you are familiar with the chain rule. Here you can see that your function h of x first let's make this clear. Function h of x is a function of another function made up of function of a function. You can see h of x is a function of f of x. And what is f of x a function of? wi xi. So can you see here? So if we are to differentiate this function, we would need to differentiate this function. And if you need to differentiate this function, then so I repeat this one more time. Your h of x function is a function of f of x. But in order to differentiate your h of x, you need to differentiate and find wx. This is the chain rule. And how we can write that? The basic definition of the chain rule is that you take the derivative of f of g of x. So you first, if we have a function that is function of a function, and so first what we will do is we take the derivative of g of x, we differentiate it with respect to this function, and then we again differentiate this function g of x with respect to x. Here we are going to differentiate with respect to g of x, and then to extract this x value, we will differentiate this g of x with respect to x. So here the chain is only 2, but sometimes we can have a further chain. Like in our case, we have 3 levels of chaining from h of x, f of x, and then from f of x you can get your w of wx. I will give you an example of the chain rule. The chain rule can be used to understand how we can differentiate a composite function. And what is a composite function? It is a function of a function. For example, cos of x squared is a composite. How is it a composite? For example, our first function can be cos of x, and our second function g of x is x squared. So we can write cos of x squared as equivalent to f of g of x. So when you place x squared here, that g of x is x squared, and then from here in this cos of x you replace the value of g of x, that is x squared, so you get your cos of x squared. This is your definition of the chaining rule, and remember this rule, we are going to use this to differentiate our function. Now we come here on this slide and we understand the chain rule. Okay, so if we want to take the partial of our error function h of xi minus yi squared error, so first we take in order to get to our wj's, we first need to take the derivative of our function h of x with respect to h of x. We extract the information from here, and then when we have h of x, we go here and find the partial with respect to f of x, and then when we have our f of x, we can finally move to our wj. So this is our chaining. One by one we are going to study each different partial. Look, this partial is very simple. So partial f of x with respect to w, and we know how we can represent our f of x, that is summation j 0 to n wi xij. So if we take the partial of this function with respect to wj, we are only left with xij. This is fairly simple. And then if we take the derivative of this function, this part, with respect to h of x, so simply derivative 2h of xi minus yi. And the next part is taking the derivative with respect to xi, the last component. Let's see how we can take the derivative of h of xi with respect to f of xi such that it is equivalent to this. Okay, we are clear with this part, and only this is left. So we will find the derivative of h of xi with respect to f of xi, and we know what is h of xi. What is h of xi? This function, which is 1 plus partial of h of xi with respect to f of xi, and we know what is h of xi, and now we are going to take the partial of this. So we write with respect to f of xi, this is important, and then we write this. So when we take the derivative, we have, this will become, this the denominator, so it raises to power, and then we have 1 by 2 whole squared, and then we have to take the partial of this next part, which is 1 plus xi. So now we are going to focus on partial of 1 plus exponent minus f of xi. If we take this derivative, we are left with f of xi, and then this part constant, it is left behind, and we are left with only exponent of minus f of xi. Okay, this cancels, and we are left with 1 by 2 multiplied by exponent minus f of xi whole squared, and this function exponent minus f of xi. Now we are going to further study this. Let's keep this on a hold, and let's see if we take 1 minus h of xi. So 1 minus 1 plus h of xi was minus of f of xi. So this becomes equal to 1 plus exponent minus f of xi minus 1 plus exponent minus f of xi. This cancels out, and we are left with exponent minus f of xi, this part, by the denominator. So now we can replace this value in this equation. Okay, we have found what is 1 minus h of xi, and this function can be converted to this format by removing this term from here. We had the squared value, so we remove it from here, and if we place it over here, one term here, then this and these are same. So what we can do is we can replace this value over here. Let's do this. We have estimated what is 1 minus h of xi, and now we are going to replace that in our equation. Okay, this is equal to h of xi, and this part is equal to 1 minus h of xi. So derivative of h of xi with respect to derivative of f of xi is equal to this, which is mentioned over here. Now replacing these three derivative partials in this equation, we are left with this part. And in order to solve the gradient descent, what we do is we have to randomly initialize them, random normal initialization. At any point you can start. For now, your understanding is enough that you can start at any point and then repeat forever for all j until a criteria is met. So this is your first wj, then eta is your learning rate, and then you find the partial such that w was equal to wt. So this equation, the value comes out to be some numerical value, 0.25 or something. Initially your value, for example, was in random initialization was 1.2, then minus learning rate is 0.25 multiplied by 0.25, your newly estimated error. Multiply these two values and then subtract. So first you had w naught, j is equal to w naught, j value was naught, so you get your w naught, and then you here w naught was there, this was your w naught, and the updated value you get is wj t plus 1. This was value at t. Okay, one more time. This is the value you have estimated for your using this function. It will be a numerical value. You will assign a learning rate, for example 0.25, and you will have a value over here when your w is equal to wt. And jth weight will be updated in this way that your new weight will be the current jth weight minus the weight at w is equal to wt, such that you have differentiated with respect to wj. So your w1 is basically minus expect your error value, differentiate that with respect to w naught, and then subtract from the current value of t that you have already, and this will assign a value to your w1. So you have a current value of w naught, then you apply a learning rate, you estimate at time t what is your value of w naught, subtract that to get your next state w1. This is how your weights are updated. So from the current weight, you will subtract the differentiation with respect to the current weight to update your new weight. At time t you had this weight, it was updated by this learning rate multiplied by the error term to estimate your new weight. This is your new weight, and this part from the equation is your old weight update of your old weight. And what is your old weight? wj at time t. What is your new weight? wj at time t plus 1. Okay. So what you are trying to do is find a function f of x that best discriminates your classifier to update your weights using the equation that is given over here, wj plus 1 with your learning rate eta, and then this equation we have already estimated, where your h of x is defined as this f of xi, and your f of xi is defined by the equation summation of wj xj. Okay, so what is the issue in this equation? If it is perfectly misclassified, then h of x is 0. So if the multiplier term is 0, this whole terms become a 0. So your weight remains the same. So how can we solve this? We find w which best fits the given data using two approaches. We first define an error and then find the w which minimizes the error function. The other one is that evaluate the probability of your d and then find w which maximizes the probability. Probabilistic function is this one, your classifier that we use using the probability, and then here we have the error function and find w that minimize the error function. Okay, so more we say that h of x is the probability of being read. Now we are going to study the probability. As x goes upward from f of x, y is more likely to be 1. So probability of yi, what is the probability that yi you have given xi and w, that your xi's are given and w's are given. So the function is h of xi if yi is 1 and your function is 1 minus h of xi if yi is 0. So either one of them will be working, either y1 or y0. So approach with probability is that you have to find a boundary that red point should have a much higher probability to be red and the blue point should have a much higher probability to be blue. This we call the likelihood function. Probability to be red is such that you have given xi and w, where xi is red, and this is the probability that your xi is blue given your input xi and w's. So in likelihood function of this type, where we have that this event occurring does not affect the occurring of this event. So if a xi point comes out to be red, it will have no effect on the rest of the outcomes. The next point can be red or next point can be blue. So in this case, the two probabilities we can multiply. Simplest explanation is this, that you can multiply these two probabilities. What two probability? Probability to be red and probability to be blue. So in logistic regression, we consider the binomial distribution where either one of the situation can be there, either yi is 1 or yi is 0. So the likelihood function over here, it is based on the Bernoulli trials, where we are aware of the success probability of an event to occur, that is P yi 1 minus pi 1 minus yi from I is 1 to n. So this is the function that we are going to use for the logistic regression. Using the probability of being red and probability of being blue. So either this can occur, either a point can be blue or it can be red. And we have the yi and 1 minus yi as the exponent in the Bernoulli trials. We can represent this in this format. We have to maximize this multiplication factor. So this is the same as likelihood of being red and the likelihood function for the xi point to be blue, such that the input is xi with weights w or regression coefficients w, and you have to maximize this. And your probability yi function is defined. If yi is red, then you define your function as h of x I, and if it is yi is 0, you define it as 1 minus h of xi, where h of xi is defined as this function w of xi. You can say that this is for y1, this is for y0, as we mentioned over here. For y1 exponent, and then for 0 1 minus yi is the exponent. So we can say here the exponent is like this. They have written over here. We can also write it in this form. So once you take the log transformation of the likelihood function, it can be simply represented in this form. So if we take the log transformation, then simply you can convert it into the summations and have the log value over here. And since we have h of xi and 1 minus yi multiplier, so this is for y is equal to 1, this is for y equals to 0. We have this function for this situation, for this condition, and this function for this condition. And what are these two conditions? When yi is 1, we have, when yi is 1, we have log of hi 1 minus yi, and when we have yi is equal to 0, we have the same function yi log of 1 of h of xi. This is for 0 and this is for 1. So if yi is 1, this term becomes 0, and when yi is 0, this term becomes 0. So this max function can be written in this form. Take this value and take this value. So this component is for red and this component is for blue, and we are trying to maximize this function such that your w result in maximizing this function. So if we write argmax of this function, maximum value, it can also be written in the form of minimum also. So when the error is minimized, we write the negative value. The more negatively it is scored, the better it is, as I mentioned in the previous lecture. So you're taking the minimum of this function now, and these are the negative values, where h of x is represented as this one. Why do we write it like this? Because we know f of x is summation of wx, right? So we can write this. Okay, now we are trying to find a boundary with gradient descent. We know that function, it is represented like this from the previous slide, and we can write h of x as a chained function, g of f of x. Why we say g of f of x? H of x basically is a function of f of x, and then f of x can be represented in this form. And how do we get from here to here? This will be explained in the next slide. Okay. We are going to take the partial of our error function, and this is the structure of our function that we got here, where h of x is your classifier. So h of x can be represented as g of f of xi, right? Log of g of f of xi. H of xi can be represented in this form. Okay, so we take the derivative with respect to w, but we, of course, this is chain rule, and first we will have the derivative of this whole function with respect to this variable. Once we get this variable, we will differentiate this variable with respect to f of xi, and when we have the f of xi, only then we can differentiate with respect to w. So now we are going to do is we are going to differentiate with respect to your g of f of xi. So we have the function g of f of xi here. For the log, we know that if we take the log of x and we take the derivative, it is equal to 1 of x, 1 by x, right? Derivative of log of x is 1 of x. So if we take the log of this one, it comes with respect to g of x, f of x. This is converted to 1 divided by this term. And then if we take the derivative with respect to this function is replaced by 1 of g of x, f of x. Okay, so this part we have understood. Next comes this part. First I will address this part, and then finally we will address this part. So this part, f of x partial with respect to w, we know it is equal to x of ij. F of x, we already know it is a function of w and x. Then if we take the derivative with respect to s, we are only left with respect to w, f of x, wx, take the derivative with respect to w, what are we left with? Only your x terms. So we have here or x term for this derivative. Now we are left with this part. It will follow the same pattern as I discussed before for h of x with respect to f of x. Now we have g of f of xi with respect to f of xi. And we know g of x is basically represented like this, and the function derivative was equal to, for this f of xi, h of x minus 1 minus h of xi. So we will replace the same method for this derivative. First we found in the previous example h of xi, and then derivative of x of xi, 1 plus exponent of minus of f of xi, and the derivative we found was h of x I 1 minus h of xi. Similarly, this h of xi is replaced with g of f of xi. So the derivative of this part is g of f of x 1 minus g of f of x. Okay. Now we have all these three partial values, and simply next what we are going to do is we are going to open these brackets, these square brackets, multiply this term with this term is removed, right? And then when we multiply this term with this, the second term will be removed, and what we are left is, from here this term is removed, and for this term removed, and we are left with, for this first part we will be left with this, and for the second part on the denominator we have 1 minus g of x, so we will be left with g of x, right? So now our function can be solved. yi minus g of f of x minus 1 plus 1 plus yi g of f of xi So these two terms, let's look at this again. Okay. yi multiplied here, and then here yi minus yi g of f of xi minus g of f of xi plus, then we multiply yi g of f of xi, the second part, so these two will cancel and you will be left with yi minus g of f of x, and then you can of course apply this minus term and change this g of x f of xi replaced with h of xi. So h of xi minus y of i is your derivative or your partial of your error function for the gradient descent. So now we know the probability based solution for logistic regression. What we can do is we can randomly initialize our w naught values, and then we can take the partial of our error function with respect to wj, and we get our new, this is your equation for update of your weight values. So you need to update. Now we are not calling this regression coefficient, we are going to call this weight values. From now on we are going to call them weight values. So weight values we are going to find, and how do we update the weight values? Optimize them using gradient descent, and this is the equation for our gradient descent. wj t plus 1 is equal to wj t minus eta, the partial that is the learning rate multiplied by the learning rate summation of h of xi minus yi, and then multiplied by your x value, and then h of xi is defined as this, and your f of xi here is defined in this way. So replace the value of f of xi and find your h of xi, subtract this with yi, multiply with xi, then sum them all these values from 1 to n, multiply by the learning factor, and update your current weight and find the new weight. This is logistic regression, and what it is used for is gradient descent method. And what is gradient descent method? Basically it is update of your weight values t plus 1, and you have your previous t minus learning rate multiplied by a function. So you have to find a boundary here such that it minimizes the error function. For logistic regression, no closed form solution exists, so we can optimize by using the gradient descent method. And here we have the binary classifier 0 or 1, and if we have more than two classes, we can use the multinomial regression, logistic regression. So it not only works with categorical data, it can also work with multi-classes, more than two classes. So in this lecture, now I will summarize. In this lecture, what we have studied is, first we studied logistic regression. What is logistic regression? Where it can be used. Then we defined a linear boundary, and we try to minimize the error using a linear classifier by minimizing the mislabeled classes. But that linear boundary had a problem, that it cannot be differentiable at certain points, and this is not favorable to update your weight values or your regression coefficients. Now we will say from now onwards they are the weight values. Next we move towards the probabilistic way of defining the boundary. Instead of the hard boundary, we define a soft classifier, and we derive the equation for our soft classifier in this form. We have a solution in the form of an equation, and this h of x is simply a function represented here, where f of x is a combination of your weight values multiplied by your input xi. Weight at point I or weight at point j, and then simply multiply it with value of input I at jth location. Now we move towards the probability based solution, where we have the likelihood function. It is based on the Bernoulli tiles, and we found how we can write this, convert from probabilistic, from the likelihood function to a log likelihood values, log values, to help us understand. This is the general expression that you will come across for the future. And then we understand what we move towards your gradient descent method, and gradient descent method is used to update your weight values. And in the gradient descent method, you have an existing weight, the current weight at time t, you have a learning rate, and you have an equation to update the values, learned values, using this equation. You put in this part, and the new weight is updated, and you go through several iterations of gradient descent. For example, this is your function. This is the local minimum value, and our gradient descent is trying to learn with each step to find this minimum value. It may find it here, and if we start the random initialization from here, maybe it takes several steps to reach at this local minima point. This is our gradient descent. For example, if we start from here, gradient random start your weight values initialization here, WJs. So gradient descent for each step update, for the each WT plus 1 update, you are moving towards your local minima. Your values can have multiple local variables. In this graph, among these 2 points, this is the lower value. It is called the global minimum value, but you can have multiple local minimum first value, and this is local minimum second value, but the smallest one will define your global minimum. I hope you have some introduction and familiarity with mathematical representation of your logistic regression. And if you have any queries, you can drop an email, and please note the slide numbers along with your questions so that we can have a good discussion on this. Thank you.